Alright, this is exam 1 for physics 202. A metallic object holds a charge of negative 3.8 times 10 to the minus 6. What total number of electrons does this represent? Okay, well we just say 3.8 times 10 to the minus 6. That's the charge divided by 1.6 times 10 to the minus 19, and that'll tell us how many there are. It's like it's 2.4 times 10 to the 13. What happens when you bring a negatively charged plastic rod, but do not touch to the end of a neutral copper wire? If I have negative charges here, I get positive charged on this end and negatively charged on that end. So it's attracted. So the wire is attracted to the plastic rod. Two charged balls are repelling from each other that hang from the ceiling. What can you say about these charges? Well, we know that they have to be opposite charges. So they're either both positive, both negative, or either one of those. In this figure, the negative Q charge sits in the middle. There's 4 charges at the corner. What is the net force on that charge? Okay, well, I can draw my force vectors. The force vector due to this charge is going to be in that direction, and due to this charge will be in that direction. So those two forces will cancel out. Due to this charge will be in this direction, and then due to this charge will be in that direction. So the... Oh, I'm sorry, excuse me. I messed that up. The net force due to this charge will be in this direction, and due to this charge in that direction. It's a negative charge here. The net force due to this charge will be in this direction, because they're attractive, and then due to this charge will be in that direction. So the net force is in this direction, which is in the second quadrant. If the distance between two negatively charged ions is doubled, the force on one of them due to the other, well, do what? Well, we know it'll decrease. It'll actually decrease by a factor of 4. That's KQQ over R squared. If I double this distance, I get a factor of 1/4 over here. So I'm decreasing by a factor of 4. This diagram shows 3 heavily charged plastic cubes. The net force on cube number 3 is shown. If cube number 3 is positively charged, what are the charges on cubes 1 and 2 respectively? Now, well, this is positively charged. You know, due to charge 1, I know the force is either in this direction or in that direction. In order to give a force in that direction, it has to be like this. So that would be a negative charge for cube 1. A negative charge giving me a force in that direction. And then due to the other charge, I know the force is either in this direction or in this direction. But in order to give this force, then it's going to have to be this direction. So if, let's see, cube 3 is positive, that means that cube 2 is also positive. So cube 1 is negative, cube 2 is positive. Consider these two charges and their resultant electric field lines. If Q2 has charge plus 2 coulombs, what is the charge on Q1? Well, I know it has to be positive because there are the field lines are coming out, and I just count the field on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 field lines, but just 4 over here, so I'm 4 times the charge, so I'm 8 coulombs. That's positive 8C. Which of these is not a unit for the electric field? Electric field is a Newton per coulomb. That's also a volt per meter. But also, a Newton per coulomb is a kilogram meter per second squared over coulombs. So that's also this. So all of these are units. So D is the right answer. All of those are units. This diagram shows 2 charges and their electric field lines. At what point is the magnitude of the electric field lines the largest? The magnitude is the largest where the field lines are closest, so that would be B. You're sitting a certain distance from a point charge, you measure an electric field of E0. If your distance from the charge is halved, what is the new electric field you measure? Well, E is KQ over R squared. If I have the distance, that means I get 4 times the electric field. Who is Dr. Young's favorite student? I don't even know who any of these people are, alright? My favorite student is me, or you, as it may be. So that was supposed to be a gimme question. Oh, and actually for this class, that question got out of order, so it should be at the end. Consider this collection of charges in the Gaussian surface. Which of these best describe the total flux through the surface? Is the flux negative, 0, or positive, or is it just impossible to tell? Well, the net charge inside this surface is positive, with a positive Q, so that means that the net flux is also going to be positive. Alright, I have This figure shows the gravitational field right here, shown by these arrows, and the Gaussian surface is right here. The surface has an area of 2 meters squared. Let's see, this calls it a line, but it's actually like a sheet. It's like a plane that it's a plane that's into the page. Has an area of 2 meters squared, and the gravitational field is 10 meters per second squared. And I want to know what is the flux. Now I know that also that they're separated by this angle theta, and I know that the flux is equal to the sum of E dot dA, or that's E cosine theta dA. So if I have an angle theta where my angle theta is 0, that is or rather 90, whereas the field and the area are perpendicular to one another, then it's equal to the flux times the area. The flux is 10, the area, or excuse me, the field is 10, the area is 2, so the maximum it could be would be 20. So is it less than 20, greater than 20, or equal to 20? Well, it's not greater than 20. It's definitely not equal to 20 as well, because I have this cosine theta term, so it has to be less than 20. The flux is actually less than 20. All right, here's the free response questions. What is the gravitational potential energy of these masses? All right, remember potential energy is G_mm over R. And I'm going to do it for these 3 pairs. I have a pair of charges here. Notice this is a 3, 4, 5 triangle, so the distance between those is 5. So I have G times 4 kilograms times 5 kilograms divided by the distance, which is 5. I'm just going to express this as 4G. Do this pair. I have a 3 and a 4 kilogram mass, so this potential energy is G times 4 kilograms, 3 kilograms divided by 4 meters. Those cancel. This is 3G. And then the last one is this 3 and 5 kilogram mass, so U is G, 3 kilograms, 5 kilograms divided by 3, that cancels. I'm left with 5G. All right, and then the total potential energy is just the sum of these. These are all positive, so it's 4 plus 3 plus 5. That is 12 times G, or 12 times 6.67 times 10 to the minus 11. I get 8 times 10 to the minus 10 joules. So not a whole lot of energy in those masses. The gravitational forces are very small between sort of, modest sized masses. All right, so in 1 or 2 sentences, actually here, let me pause for a second. Okay, so let's see, in 1 or 2 sentences, describe Newton's shell theorem. I accepted a range of answers on this, but basically it's that a uniform shell of matter attracts a particle that is outside the shell as if all the shell's mass were concentrated at its center. So a uniform shell of matter, spherical shell that is, attracts a mass outside of that shell as if all the shell's mass were concentrated at its center. Alright, in short, I draw a little picture here. So if I have a shell of matter like this, and then I have another mass over here, this would be the equivalent picture of having that shell of matter collapse down to a point, and then that other point. So this shell of matter looks like a point mass to this other mass that's located over here. I can treat that shell just as a point mass. All right, what is the acceleration due to gravity at a distance of 100,000 meters above the surface of the Earth? Okay, well I know that G is equal to GM over R squared. All right, that's on the surface of the Earth, but this is above the surface of the Earth, so it's GM over R plus H squared. And so let's see, that's 6.67 times 10 to the minus 11 times the mass of the Earth. I don't know right off the top of my head. It is 6 times 10 to the 24 divided by the radius of the Earth, which is 6.4 times 10 to the 6, plus that height squared. And then you want to solve that for h. Excuse me, no, h is given here, 100,000. So this is 10 to the 5th. All right, so let's see, we get 6.67 minus 11. I get 9.47. So at 100,000 meters above the Earth, we're at 9.47 meters per second squared is our acceleration due to gravity. That's our gravitational field, 100,000 meters above the surface of the Earth. All right, 17, a 3 coulomb charge is accelerated by a constant electric field of 16 newtons per coulomb. The mass of the charge is 2 kilograms. Find the acceleration of the particle. And what is the particle's displacement after 2 seconds? All right, so first of all, I want to find out what is the force. See, I'm going to go to a darker color here. The force is equal to 3 coulombs times the electric field, which is 60 newtons per coulomb. That gives me 180 newtons. And then my acceleration, which is part A, is F over m. That's 180 newtons divided by the mass, which is 2 kilograms. That's 90 meters per second squared. And then in part B, I want to know what is the displacement. But x is just 1/2 at squared. That's 1/2 of 90 times t, which was 2 seconds. That's 180 meters. What is the magnitude and direction of the electric field at point A? All right, so I have 2 charges. I have this charge. The magnitude of the electric field, which I'll call E1, is in this direction. That's the same direction that a positive particle would feel a force in. I can go and calculate what E1 is. It should be kq over r squared. That's 9 times 10 to the 9th. That q is 16 times 10 to the minus 9 divided by r squared. That's 4 meters squared. This cancels with that, that with that, and we're left with 9 newtons per coulomb. Then if I want to do the other one, at this point, due to this charge, my electric field is in this direction. I'll call this E2. kq over r squared again. That's 9 times 10 to the 9th. Q is 6 times 10 to the minus 9. Notice I don't put the sign here because the sign is already being included when I draw this velocity vector. Divided by the distance, which is 3 meters squared. That cancels with that, that with that, and we're left with 6 newtons per coulomb. All right, so I have vectors here. I have one vector that's 6, and another vector that's 9, and then the resultant vector is here at this angle. I want to know the magnitude and direction. This magnitude is the square root of 6 squared plus 9 squared. Let's see, that is 11 newtons per coulomb. And then the angle theta is the inverse tan of 9 over 6, which is 56 degrees below the positive x-axis. That's the answer, 11 newtons per coulomb at 56 degrees below the positive x-axis. I consider this dipole, what is the label the electric field and equal potential lines? 6 field lines and 6 equal potential lines. Actually, we can just do 4, it's fine. I'm just going to do 4 here. All right, so I have field lines go from positive to negative. Actually, I'm going to do 8. But because this is twice the charge, I get twice as many field lines. So, all right, and then if I want to draw the equal potential lines, they look like this. Always perpendicular to the field lines, so always at 90 degrees to the field lines. Something like that. All right. Last question. I have this cube. Electric field is given right here. What is the net flux through the cube, and what is the total charge enclosed with the cube? Well, first of all, the net flux, I first want to figure out, since this electric field is only in the I and j direction, what are those parts of the cube that have 0 flux? And those will be the parts of the cube that have area vectors in the k direction. So the front and back faces have 0 flux. For the front and back, phi will equal 0. Remember, that's because E dot dA is equal to 0. The dot product is equal to 0. So if I take the integral of 0, of course that's 0. All right, so now if I want to know the top, let's do the top. In the top, the area vector is in the positive j direction. So my flux is equal to the integral of E dot dA. That's 2I plus 3yj. Dotted with dA in the j direction. So this is going to be the integral of 3y dA. At the top, y is equal to 3 because this is a 3 by 3 by 3 cube. So I have 3 times 3 times the integral of dA, which is 9. The integral of dA is just the area, so this can be 9 times 9, which is 81. My flux is 81 Newton meters squared per coulomb. All right, now let's go ahead and do the bottom. But if I think about this in the bottom, I don't really need to do it because in the bottom, it's going to be a little bit different. I'll have a negative dA here because it's in the bottom, the area vector is in the negative y direction, negative j direction. But here, y will equal 0. So since that y is equal to 0, the flux will equal to 0. So in the bottom, the flux is equal to 0. So now let's do the left. That's on this side. In this case, dA is equal to our dA is in the, what is that, negative I direction. So my area vector is negative dAi. So if I'm finding my flux, then it's going to be the integral of E, which is, what was E? 2I plus 3yj, dotted with negative dAi. All right, so that's going to be negative 2 integral of dA, which is negative 2 times 9, or negative 18 Newton meters squared per coulomb. Okay, that's the left face. Now let's do the, let's do this purple. The right face. On the right face, my area is going to be dA in the positive I direction. So my flux then will be the integral of E dot dA. 2I plus 3yj time dotted with dA I. That's going to equal 2 dA which is equal to positive 18. All right, so now if I add up all my fluxes, let's see, I have 18 minus 18, I have 0, 81, and then I also have 0 and 0. So I have negative 18, I have plus 0 plus 81 plus 0 plus 0. And so of course that's just 81 Newton meter squared per Coulomb. All right, so that's the first part, the flux. And now I want to know the total charge enclosed. Well, by Gauss's law, it's just equal to epsilon naught times the flux, which is 8.85 times 10 to the minus 12, times the flux, which is 81, and that's equal to 7.2 times 10 to the minus 10 coulombs. All right, so that's Gauss's law. I think that's the last one. There's the answers in multiple choice. Again, I'm going to change the order on your test, so the order might be slightly different. The answers actually multiple choice.